Start recording. Okay, so I'm back from holidays and we are back after a short break doing more user interface stuff. So where we left off, it can be an oddly sized drawing today. Where we left off, we were going through and expanding out our API. So we got to a situation where, we've got too many parameters. We just want one ID, which is going to be the text field. And if you want more stuff, we'll do the hashtag thing from ImGUI, and we're also going to add this next ID thing, so we're not generating string-based IDs from integers. Like, we don't have to call toString, we don't have to spin up a string builder, and so on and so forth, to add IDs to the system. Basically, we're avoiding garbage collection and allocations by doing this. So there's a couple of things we want to do, and I think what we want to start with, so we're pretty happy with the API. On the outer layer, we're now
kind of missing one of your methods, actually, just to be.
Oh, I think it's just this with string builder.
Yeah. Oh, I see. Okay.
Yeah.
Fair.
So I'll scroll back down to it in a sec. But it's basically the same. So on the outside, this is like our usage code. We are now garbage free, which is nice. Do the hashtag thing. Oh yes, so we're going to do the hashtag thing shortly. But down here, so API is nice. We have a problem here. We're calling toString a whole bunch on string builders, which is obviously a problem because string builder doesn't hash nicely, oddly enough. It doesn't give you the hash of the string it contains. It gives you
right. This is the runtime helper.
Hash. Yep.
Yeah, reference hash.
Yep. Which is, I guess, how it's supposed to work, but it's like kind of silly. Like, I don't think get hash code was necessarily a smart choice. I guess they have to do it if they have a dictionary.
Yeah, that's right. Although the name could be, they could have called it something different, because obviously it's not a hash code. It's not based on the values inside the object. Like, you have to override your hashtag if you want to do anything meaningful.
So anyway, so then we get into update, and we've got all right, we're doing the same thing here. We have to convert it to a string to get a sane hash. Same thing again. So we're gonna have to do something about that. So getting a hash from a string builder is something we need to solve to get rid of this garbage. And what else? So we come down here, we've got the same issue here. Working toString. We seem to have the same issue here. Internal get ID text, that's fine, but this is a problem. So it all seems to come down to, looking at our code now, to the fact that we are hashing strings, and we're just dumping it through the string.get hashcode, like, built in. So the first thing I wanted to mention is something we were talking about the other day. All right, so the Wikipedia page for something called the pigeonhole principle. And basically, this is the idea when we have a hash. You can sort of think about the statistics of hashing. I think the birthday problem is actually the issue that we have when we do this. But we're not going to actually go through this in any sort of detail, but I just want to point out the idea. And the idea is, like, if we have 9 possible results from the hash, we can only store 9 possible things. So if we have 10 items, we're going to have a hash collision, essentially. And sort of by the same token, even if we only have 2 items and they're both hashed to the same thing, we will have a hash collision. Now, of course, we have 2 to the 2 to the 32. So we have 4 billion odd pigeonholes if we have a 32-bit hash. So our chance of actually having a collision is quite low. So we can sort of think about this from the perspective of we have 4 billion pigeonholes with our hash that we're getting from item ID. And we have up here, we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, let's say about 20 odd items. So we're trying to fit 20 items into 4 billion holes and hoping that none of them collide. That's sort of the way to think about it. Does that make sense?
Yep.
And I believe that the birthday problem is the way that you calculate like your odds of having a collision, like just with random strings, which is not what we have, although the hash function tries to make strings as effectively random as possible. So that's the sort of thing we talked about before, was like an avalanche function, I think was we were looking at, is like you add like a small change, like you change one bit in the thing, and ideally about half the bits in the resulting hash will change, pseudo randomly. So you can sort of think of the strings, even though the strings are not random, as random when you're hashing them. And then so if you have 10 random items getting inserted into 4 billion boxes, you know, how likely is it that you'll collide? And you can work that out. And it's like, well, it's, you know, 1 in, I don't know what the actual answer would be, because I haven't done the maths and I'm not going to, but it will be quite low. It's like maybe 1 in 100 million or something.
That's interesting, because I thought that because we control the hash function itself, that we would be pretty much guaranteed not to have a collision because we're using a specific function. But I guess that's not true. Like, you could technically hash 2 different values and get the same hash.
Yep.
It's just so ridiculously low probability that it almost seems certain that even if you control the function itself, like how the hash is built, that you could actually still get a hash collision on this that's crazy. I like that.
So that's it's basically a probabilistic thing. So there's 2 ways we can deal with this situation. Excuse me. One, like, so I wish I had done the maths ahead of time, but I haven't. But like, I was guesstimating that it's 1 in 100 million chance that we'll get a collision, which is pretty low. And we might be okay with that. But say we weren't okay with that. There's 2 ways we can go. One way is we can store the input values somehow, which, you know, is going to require a fair bit of storage. And basically hope that, guarantee that we'll never deal with a collision, because if you get 2 hashes that are the same value, we then check, you know, the exact string that was input and the, you know, the next ID that was input. So we actually store all the information. So that's the basic thing that something like dictionary does, is it does a hash lookup, but when it does a final key matching, it will actually match the keys exactly before it returns to you.
Okay.
So it could do it that way, which guarantees us that, but it requires a lot of storage. The other thing we could do is we could just crank up the number of bits. So we've got a 32-bit hash here. So if we did a 128-bit hash, where's my calculator? 128. 2 to the 128 maths. So that's really big. It's an enormous number for sticking 20 items in. And I think like the argument that a lot of people make, particularly once you get up to 128 bits, is like, well, that's like, and I don't know if this is actually true because I haven't looked it up, but it's sort of a argument from, you know, there's more atoms in the universe than there are potential output hashes once you start to get up to this number of bits of hash.
You
So
mean less atoms in the universe than
yes,
potential?
sorry, yeah, fewer atoms in the universe. So it's
Right.
like, so your chance of
Probably good enough for this universe.
yeah, so your chance of
It's
colliding is really, really low, or at least you know when you do the birthday paradox thing, um, if we're sticking 20 items into this, the reason I don't think it's a straight division. I don't think you can just go divide by 20. I think it's actually a bit more complicated. The more items you have, I think is it exponential? I can't remember. I wish I could remember. Anyway, it does actually like the odds reduce. What is it? Superlinearly. Anyway, suffice to say, like the more items you have, the more likely you have a collision. But like a number like this, like even like this is still ridiculously huge, and we're never going to collide. Like just as a matter of practicality. So that's because we don't want to deal with storage, and we're quite happy with our like hash situation over here, which was, if I can find it, this is a hash. Like if we can expand this out to 128 bits, we deal with this problem. That's one line of logic that takes us down the road of we're going to implement our own hashing function. And the other one is obviously we need to do something about the fact that like this is a like pain in the neck. This is a disaster. We actually do need to do something about this. So then we want to make our own hash function. So we wriggle on over to this Wikipedia page and be like, all right, well, what are the options? And we don't want a cyclic redundancy check. I don't know why you would want one. Actually, I guess you would. I can't remember now. I think it's like a streaming thing, or a checksum. We want like a hash function. Anyway, so these are cryptographic ones, which we don't care about. We want a fast, non-cryptographic one. No one's added meow hash to this yet, but we also don't want to drop into native code at the moment. So basically, it's a matter of like just going through these and choosing one, and we want to choose one that's got like at least 128 bits. In fact, we probably don't want more than 128 bits because that would be slower and use more space. So
it's going to be murmur hash.
It is going to be murmur hash, and you can tell because I've already looked it up. It's also, this is what we used on River City. So I've already done this process of like going through all of these and seeing how hard are they implement. That was a big one. It's like I just want a hash function. Don't make me set up tables, and I think Jenkins is the other one we used on River City. And I don't want to set up tables. I don't want to do operations that are a pain in the neck in C# to do. So I think Jenkins on Murmur is. In fact, we may do Jenkins because it's actually really simple. If we get enough bits on Jenkins, 64 bits. We could do. We could.
Oh, right.
We could say 64 bits is enough. I mean, 64 is to the 64. Like, it's still huge, and that solves our problem. And I don't want to spend too much time implementing someone else's code.
Yep.
So this is the avalanche behavior. So you can see it's quite good. Like it's like so you can think of these as pigeonholes. It's like one pigeon per hole until you hit like because you've got more pigeons than you have holes. So these are the holes it fills up, and it only fills them up once. I think, is that what that means? I think that's what that means. I can't remember now. All right. Anyway, so this is Jenkins. I think this is why I use Jenkins in one place on River City, because it's like so simple to implement. Murmur hash is a better hash, and this one this one's a bit more complicated. And I think I use murmur hash for a higher quality hash on our asset pipeline.
Right.
And so that's a situation where you actually want a good fast hash. This is where it's like, I don't care, just slap it together. So let's slap it together. Let's do Jenkins. And so this is what we're going to implement. And so I don't know how you want to do this. If you want to like put this up,
I'll just bring it up on my.
down
I'll
on
bring
your
it up on
other side of your screen.
Well, I guess that doesn't really help because then it'll block your screen.
I'll bring it up on mine, and so I know what we'll do.
Well,
we'll shrink
I
down
think I
here,
can
and we'll do this here.
All right.
So I've got it on mine, so yeah, you can cover what you need to, and like this will be good enough, and we'll do it in. This is the 32-bit version. Where's the 64-bit version? Spooky hash. Oh, okay. So maybe.
Oh, spooky hash is just the name of Jenkins 64. Yeah, it is. Okay.
Normally, you get the implementation of these on Wikipedia, but all right, we're gonna do the 32-bit version because.
Yeah, it makes sense.
Because you recall what we have to do if we want a 64-bit type is easy to do in C#, but a 128-bit type is like you got to start doing a struct and worrying about it. But let's do 32 for now because
it's like a struct of 2 ulongs, right? I think you built that into the serializer, like value 128. I think is what you called it.
Yeah. So anyway, we're gonna do this one just because it's so simple, and this is sort of the exercise is doing this rather than sort of worrying about implementing someone else's code. Now, so to stop you right there, ulong is 64-bit value.
Oh, right. It's a 32-bit hash. It's just 64 bytes of data. Wait, hold on a second.
No, it's any number of bytes of data.
Right, and that's what this is. That's the size, basically, like how much.
So in fact, what I'm going to do, I'm just going to copy this in. Let's do this as a bit of an exercise. Let's convert this to C# from C. Because that's probably an interesting thing to do. Okay, so if we were to talk about how much C coding have you done? Like, not a lot, yeah.
Yeah, I took it in university in like 2005.
Like
2000.
We could look up the Wikipedia page because it's just so easy to look up these things on Wikipedia. So this will tell us like a lot of the data types are, but it doesn't tell us size T, which maybe is a C++ thing. Let's see if there's a Wikipedia page for that. No, all right. Anyway, I know these, so we'll just go through them. So uint32.
So already,
you're just writing this out by hand.
Yeah, I have to. Oh, I don't have to actually, because of the power of the internet. I too can copy and paste.
Never copy paste codes, kids. Kids. So let's go through. So uint32t is just like the disaster of like, in fact, the exact page that I had up, which was this, like, character, signed character, unsigned character, short int, short, signed short, int, unsigned short, like this garbage here, where it's like, where is it? Capable of containing at least 16 bits of data. Like, this nonsense. Eventually they came up with, and let's see if it's there. So types.h, int types.h, there it is, yep. So then they actually like, all right, let's actually solve this problem, and then they added these things, which actually tell you exactly what the size is, and then they have to stick an underscore T on there because everyone and their dog normally just defines these when they program in C. So everyone's got that already in like their company's standard header. We, on the other hand, can just do this. Now,
I'm surprised it's not uint, but I guess because
Oh yeah, sorry, my bad. It actually doesn't matter. We'll have to think about that actually.
I always figured uint for hashes because you want the extra.
Yeah. Well, no. Okay. So let's jump forward a little bit.
Sure.
This shift here. So this will be uint as well. This is a shift right. There's two kinds of shift. Like shift left is always shifting left. So if we have a number like 0, 0, 1, 0, I don't know, like this is 8 bits. Okay. So if we have an 8-bit number like this, and we want to shift it 2 places to the right. So we go shift, sorry, to the left, shift 2. We get this. Okay, so this is effectively the same as multiplying it by, we can do this with calculator because maths. So if we have a value in binary of 001110101, and we do so it's 53, and we do a left shift by 2, we get 212, and you can see the bits in here have shifted up. But the thing is, if we put that in byte, like if we put that in byte, you see that this is the sign bit, and so the question is, when we shift it to the right, so this is 212 or negative 44. When we shift it to the right, do we treat that as signed or unsigned? If we treat it as unsigned, we get 212. We shift it left by 2. 212. We shift it right by 2. We get 53. We get the original result back. So 2, we get this. But if we do 2 as a arithmetic shift, we do what's called sign extension, and what that does, this is 53, do a sign extension, and we have 212 bytes, we shift right by 2, we get negative 11. And this is 11110101, and so what you see that it's done is it's taken this upper bit, and it's copied it into the shift location, whereas this one has inserted zeros. So that's logical shift, insert zeros. Arithmetic shift copies the sign bit. Does that make sense?
I think so.
And so what happens is we've got this is negative 44. So this is effectively multiplying by 4. So 53 times 4 is, hang on, put that into something wider. 53 times 4, we get that. And this is effectively dividing by 4. Is shifting right by 2. So this multiplication and shifting are sort of the same thing, in a sense. So if we shift left by 2, we got 44. We've got 212. We divided by 4. 212 divided by 4. We get 53. But negative 44 divided by 4, we get 11. And these are obviously the bits for 11 has all of this stuff at the front, whereas the bits for 212, that's basically, this is unsigned. It's this. Signed is this. Hang on, what have I done? No, this should be negative 11. That's better. Yeah. So does that all make sense?
I think so.
Yeah. So that's all about how these numbers are stored in binary. So they call that, you've probably heard of it. 2's complement.
Yep.
And so you can see it's like there is a sign bit, and it starts from like -4 if it's a 3-bit number. What the heck? Oh yeah, binary tricks. I was like, what is this? Yeah, this one. Anyway, so that's what that's all about. So that's why we have to make it a uint, because otherwise we are sign extending, and I suspect that's going to cause this to give us the wrong result. I'd have to actually think about how that would affect the hash, because we're doing an exclusive OR, so it might not actually make that much difference. But certainly the implementation that was provided does insert zeros there, which I think is probably better, because otherwise you're copying a bit across multiple bit positions, and I think that is not good. But that's sort of something I'd have to look at with how hashing works, which is not my sort of area of expertise. So okay, we have size ti. So this is int. This is basically int pointer. In C# is size t. So size t.
Size of t.
Yeah, no, sorry. Size t. So this is effectively the same as a pointer wide integer. And so the same thing here. And then, so what we have up here, uint 8. So this is actually byte. So this is in fact, and we have the length. So byte array already comes with the length, as you've seen. So we can get rid of the length value. So while I is not equal to key of length, increase I, and then we notice that array length is actually a 32-bit integer in this case, so we don't actually care about the fact that it could potentially be longer. So this is I think this is a holdover from like C# or .NET 1.0, where it's like long length. So if you actually want to be 64-bit happy, you can use long length. But obviously we're not going to have any strings that are 64 bits wide, so we just use length and make the code simpler. So this is now we've converted the function, and you can see all the red squiggles have gone away. So this is the Jenkins hash.
Okay.
And we get out a 32-bit hash for a byte array. Now, what we have a small problem with is that's not exactly what we want, because we are trying to get the hash code of we're trying to get the hash code for several things. We want an integer, we want a string, we want a string builder. We want these two to give the same result, ideally. Like if you pass the same string as both a string builder and a string, I think it makes sense to make it like output the same result.
Yep.
And we also want to have the ability to yeah, so we want this next ID hash, and we could just do it the way we've been doing it. We just XOR the two hashes together. But the other thing we could do is we could append through the Jenkins hash. But I think the simplest thing to do is probably just to do it with the XOR that we're already doing. It's like give me the next ID, and we'll get the hash code of that and XOR it with the ID hash. Because we've got two hashes, we'll mash them together using that method. That's easiest. So let's basically what we'll do, I think all we need to do is take the Jenkins hash, and we should make it take a string. We also want it to take integer and string builder. I've done this in a weird order. but I'll fix that now. But we don't need to take a byte array because we don't have a byte array. So we've got a bit of...
String is a character array, I assume, technically, right?
Yeah, so string is made up of characters. So we've got a small issue here, and that is the hash. In fact, we could think about this. We're taking in 16-bit values as the input here. So we could think about that. Let's just keep going with it. I know it's not ideal. So I think one of the things that the murmur hash does is it collects up. I'll just bring up murmur hash for a sec. I'm sort of fudging through this bit of code because I haven't really read it, but it looks like, if length is greater than 3. So what it does is it chunks it into 4-byte chunks and does the hash on that. And then whatever's left over, the last, 0 to 3 bytes, it does like this special padding thing.
Right. Padding it so it's aligned.
Yeah. So, whereas we have sort of the opposite. So, if you're doing murmur hash, you have to actually do something about the fact that it's not an alignment thing. It's like the hash works in int32 size blocks.
Okay.
And you have to do something with the end, so it just pads it. So it's it pads it so the end is a 4-byte chunk. I think it does something to it, whatever this is. I think it just pads it with zeros effectively. I'm not sure exactly. I haven't looked at that in too much detail. So we have to do sort of the opposite. We have to actually deal with the fact that we're getting on each I we're getting a 16-bit value. So let's start with string because that's probably the easiest one, and then we'll do the others.
Well, it kind of works the way it is, doesn't it? I mean, we're pulling out a byte, which is we're pulling out the character, which is intrinsically, right? Or it's overloaded.
Well, I mean, let's rock on over to string and have a look at what this returns. So the indexer returns a character, and if we rock over to character, we notice that it is in fact 16 bits long.
Right, but we need a 32-bit one, right?
No, we need an 8-bit one.
So this is actually, this is a pretty well-known problem that in the web world that .NET doesn't, or .NET can't parse UTF-8 strings natively. It has to basically load them in as UTF-16 and then parse. That's kind of like a problem for performance.
So that's I used to know the exact history of that, but basically it's a holdover from Windows NT.
Okay. So basically we need 8-bit. We're getting them in 16, so we have to basically cut or double the size of the string, or what do I mean by that? Oh, I hope this isn't a Unicode problem, because code points and all that.
So we just want to pretend the string is a
8-bit string.
8 bits, like an array of 8-bit values, an array of bytes.
Right.
But we've got an array of 16-bit values. So there's a fairly simple transformation. Well, bit converter is going to like allocate and do awful things, and we can actually do this really simply. So we're actually going to do a bit of like shifting and stuff. So
okay. Yeah. That's not. Yeah. I have no idea.
Okay. So let's think about
conceptually. I understand.
Let's think about what we've got here.
Mm-hmm.
We have so we have this is our character, and we've got that, and we've got this, and so this is this will be the upper, and this will be the lower. So this is sort of what we've got in memory. We've got 2 bytes next to each other that form a single character. We've got the upper 8 bits and the lower 8 bits of this character. So these are bits. So does that make sense so far?
Yep.
And so let's look at what we're actually down here doing with them. What if these were bytes? We'd be taking out a byte, we'd be adding it to the hash, and then we'd be doing a couple of operations that are not really relevant. So what we want to do here, we want to replace this accessor that's giving us a character with something that's going to give us a byte, and we want the lower byte, and then we want the upper byte. So I guess the first thing to do would be, can we just ignore the upper byte for a moment and just grab out all of the lower bytes? So do you know what you would do to do that?
Well, I want to shift everything to the left so that 0 or the 0 of the lower byte is the first value. So, right? Like we're moving it in place.
I think that's, well, I'm saying let's do the lower byte first.
Yeah.
And I've kind of just banged this together. I'm just trying to think about how it would be laid out in memory. So it's more like, because you start with the most significant, hang on, we're big endian, little endian, no, we're little endian. So in memory it's actually lower, and then upper, and then this goes I don't want to explain little endian at the moment because it's annoying, but and the thing is you don't actually have to think about it, so I'll just pretend we're big endian for a second, for a moment, and so really it's like 7 6 5 4 3 2 1 0. So this is like bit 0 tells us, you know, like if the value, if the character is 1, like if this is the numeric value, then that's going to be equal to it's like effectively that, for example. And then if we have a value of like 3, it's going to be that, and so on.
Yep.
And so what we want to do is we want that one, and then we want that one. And so we'll just concentrate on that. We'll pretend this doesn't even exist. We'll just strip it out for now. So on every character, we just want that. And so if we have a value like that, we're just going to ignore that. We're just going to forget about that for now. So let's just pretend this is 3, effectively, if we happen to have a character that does that. So coming back down to here, the question is, how do you extract out just these bits? Because really it's like mushed together like that.
Yeah.
We want to unmush it. So do you know what operation you would do for that?
Is it one of the XAND or XORs? I think it's XOR, isn't it?
Well, let's look at the different options. So
we're trying to distribute away all of the bits on the left so that they become zeros, right? That's how we're effectively.
Yeah, so all of the upper bits, we're trying to make those zeros. So the options are AND or XOR, basically. I mean, also,
there's no XAND.
There is no XAND. Yeah.
Well, there is now.
Exclusive AND. Actually, that's an interesting question. I bet it's something weird.
Well, XOR has that cool property where, like it flips. What's the thing you were showing me the last time? It's the only one that it can be done.
Oh, there is. Yeah, I'm just like, there's no exclusive. There is an exclusive AND.
Yes.
It's bitwise equal. It's basically, it's not XOR, I think. Is it? Yeah. I think so. I was like,
I feel like I saw it once before, but
because I searched it on Wikipedia, oddly enough, and it's like, yeah, it's XNOR.
Schnorr.
So, XOR that, or you can stick it there, not XOR. And it basically gives you equality. It's like, if you look at the truth table, it's like, if it's true and it's true, it's true. If it's false and it's false, it's true. But if it's false and true, it's false. False and true, it's false. So it's like, if the 2 bits are equal, it gives you 1. Otherwise, it gives you 0.
Huh. So
Which
2
is,
wrongs do make a right. That's interesting.
So it's basically the inverse of XOR. And in fact, you can see this here. Can you have a link to XOR, please? XOR, yeah. So you can see, like, this is the logic gate if you're building a circuit. It's like, this is XOR,
yeah.
And it's like, it's XOR with a not on the end. So it's basically the same. This is why you don't really see it much. You don't need it.
Right. It can always be expressed as equals or whatever.
Yeah. So you can either express it as a inverse of, like, you just apply these 2 in sequence, or you just use the equality operator if you want to. Was I using logical before? I should have written bitwise. Anyway, yeah, if you want logical equality, you just use the equal symbol, and if you want bitwise equality, you just, I guess, you do that.
Right. Well, we want the left side to go away, or the upper to go away, so I don't think it can be an and. So I feel like it's got to be the. Well, if it's XOR, maybe it will shift. So maybe it's just a regular old bitwise or good old pipe.
Well, okay. So let's say it's bitwise OR. What would you put as the operand? So this is that. It's like OR something is equal to that. We've got basically our equation here. So, and then we'll figure out what the result is. So what would you stick in as the second operand?
Hash squiggly, or sorry, a hash
squiggly.
right 8. No, I don't think so.
So these unfortunately computers can only store 1 or 0. So
oh yeah.
So these are bits.
Oh, that's their problem, not mine. Oh yeah. Okay, sorry. You're asking me in bits. Okay, so oh, okay, so right. What are we doing again? We're dissing and oring this is equal. Oh yeah,
cut this
what
off.
operation are we
let's figure out what we want the result to be. I think
well, we want it to be
0,
0, 0, 0, 0, yeah, and then the 2 1s at the end. That's clearly what we're after. So it kind of feels like the right hand operand's probably 1 1 1 1 1 1 1 1 1 1. No, the one that's the left hand one.
Yep. Okay. Oh, sorry. Yeah.
We want that one to be all 0s and the other one to be all 1s.
Right. Oh my. All right.
Yeah, so, that's what I think. But
so that's what you think, and so
yeah.
Well, now this is what it actually does. So if you do this, and we are doing OR, so it's like that or that.
Oh, I think.
And what you're gonna get is that, and then.
Oh God, you're right. Yeah, I screwed this up.
So that's OR. So let's try.
Not OR. So it is the XOR then.
Okay, so XOR. So XOR of that is like, well, that will give you. You're not going to like this. It's going to give you.
1 1 1 1 0 0.
It's going to give you that, as you see.
This is fun. Let's try every single one, I guess. Okay, let me actually think about this. Like, it's not because not's just going to flip everything around.
Yep.
It's going to make the 1s 0s and the 0s 1s. So it's clearly and. Oh my God, it's so and it's ridiculously easy that it's and. Yeah, it's and.
Yeah.
It's the only one left, but also it's obviously and.
Yeah.
Because I wasn't thinking about this at all like a truth table. Clearly, the only possible option is where the 1s match. That's where we want 1s to come out. So, derp.
So just to exactly. So just to sort of give you the way of thinking about this. Or is like combine. And I don't know if you like have like a notebook or something that you
Oh yeah,
write these in.
no, I don't. I know this is just.
XOR
Yeah,
is.
I know these things, and I just completely.
How would you conceptualize XOR? It's like hash combine. It's like, so this is like,
Right.
So this is how you sort of get the opposite process. So if you've got like, this is the upper and maybe you've got like, this is the lower. This is how you would get like, this is how you combine two things to get a combined output. And
Right.
and just like mask. It's like, I want to mask out these ones. I get this.
Yep.
So that's how you think of all of these. And then not is obviously just flip.
Wow.
So now we have that.
Still bathing in my own stupidity here. Just give me a minute.
Well, that's all right.
With some loose stuff. No, it's just like I did that stuff in school, like the truth table stuff, and I know what OR is and and stuff because I program computers.
So,
but whatever.
Like this is how I think of it. It's like combine, hash combine, and mask.
Yeah, I like those. I'm gonna have to write those down. Yeah. Don't need to write the other one down. Okay.
Yeah. So and then yeah. Okay. So back to this. We're doing the Jenkins hash of the string. We want to do the and this. We want to do this operation on this. And so, how would you program that? Just to
Well, we're gonna need two.
Okay.
Upper. Right, because we have to get the first 8-bit.
Well, let's worry about the upper ones next. So we'll start with the lower ones.
I'm not quite sure what you mean.
I completely ignore this. We're just getting rid of this for now. The upper side. So don't worry about the second one yet. We'll just do the lower ones for now.
Okay, gotcha. Yeah. So this value here, we want to mask the upper bits out. So that would be. Oh, hold on a second. This is incrementing inside. I don't like that.
Yeah, that's kind of awful, isn't it? Let's make a for loop there. One reason that's nice, like just a little tidbit, one reason it's nice to use a for loop here, while might work, but a for loop, I know for a fact that the JIT will actually skip the length comparison. No, is it skip the length? Oh no, sorry, it won't skip the length. It will skip the validation for this section. It will skip the range check because it knows that this is never going to be range.
It's already in there.
I don't know if it'll do that for a while. It might, but well, it may as well do the thing we know is guaranteed by the runtime. So we'll get rid of that business. You're quite right. That was quite ugly. So we're ANDing something.
We're ANDing the thing. Oh, we're ANDing both bits against the what were we ANDing? We're ANDing both bits by just the lower bit. Wait, what? But then we don't
make sure you look at my screen. So
yeah, we're ANDing it by
this is key I.
Yeah, and then this is the special value, which is basically yeah. So yeah, it's whatever that value is. But in order to get that value, we probably express it with the bitwise stuff, right?
Well, there's a couple of ways we can do this. So, any thoughts, or is, like, this is just a syntax thing? So,
It's just yeah, I don't exactly know, but we're expressing the constant of a 16-bit value that's half full of so it's like let me think about that. Well, wait. So what's the 16 bits? That's like U short
Well, I'll tell you a
max shifty. I don't know.
I mean,
Go ahead.
that's a way one way to do it, but we're gonna do it. We're gonna be a bit more concise about it. And
Okay.
let me show you a good way to do it. So what I want you to do is pull up calculator, and hopefully, oh god, Windows 10. So goodness knows. See if it still works the way the old one does, and press Alt 3. Ah, it does. So now we've got the programmer calculator. What, really? It's not nearly as nice as this one.
No, it isn't.
Oh, okay. So, see, the thing that's actually really annoying. So what I want to do is like, all right, here are the bits. We can just click them.
Oh, I think I can do that.
Oh yeah, sweet. Oh, okay, yeah. So you can actually just click the bits and turn them on or off.
Oh, yeah. We want 8 bits. That's all we want.
Yep. And so
So
that's that.
go
And you
back
can
to
see
250. Well, 250. Sure,
255.
255.
So traditionally,
Well,
you'd
I
use,
could have counted that myself, but I forgot.
yeah. So traditionally, you use the hexadecimal for this. In I think the newer versions of C Sharp, you might even be able to do this. Obviously, I'm on an old version, so that's going to whinge. But you'll notice, like, if you look at a whole lot of code that I write, you'll see stuff like this, which is just that in hex.
Great. Still complaining.
So
Can't convert int to uint. Oh.
So we know
Right.
now this is a just a weird language thing. We know that this is giving us a character, which is an unsigned integer. But then to do the and is I think character is unsigned, and then to do the and is converting it to an int when it really should convert it to a uint because it won't do a 16-bit bitwise operation.
But why does mine work? Mine, I just threw a u on the end to just describe OXFF
okay.
as the literal.
That also works because this is ambiguous. It will silently convert this to whatever it needs to
Right.
be.
Well, but basically, I'm casting the right hand side. You're casting the left hand side.
In fact,
I like the U just because it's less typing.
yeah, it's like you, and you know, it's a
F you.
Yeah, I was like, that's all over. It's all over the code. And I'm like, this is satisfying.
Oh, I don't think you don't have to cast the left anymore if the U is cast, right?
This is one of these things like I actually like just leaving this cast in here.
Oh,
So
okay,
like,
sure. Yeah.
It's like, oh, yeah, I actually want this to be unsigned. Definitely make this unsigned. Although, actually, strictly speaking, it doesn't matter. Because we're not even operating on anywhere near the signed bit. We're only in 8 bits.
Oh, yeah. Okay, right.
So if I mouse over this now, it's not going to tell me.
Cool.
So I just, yeah, suffice to say, the runtime and the JIT will elide any excess casts either way. If you're like, oh, it's assigned, oh, it's an unsigned, oh, it's signed, oh, it's unsigned, it'll actually get rid of all of the nonsense.
That goes back to the principle that code should be readable, not concise to the point of losing readability.
So, yeah, that one doesn't really matter. So now we have got the lower bits. So basically, we're just chopping out the upper bits. So now we need to do something with the upper bits. So we're back here, and we want this section. And not only do we want this, like, well, you tell me, what do we want as the result for the next section? I'm just going to take this and we'll stick it down here. This is... So let's copy in one of our
Right,
equations.
but we want to snap off the upper half so that we can do the same thing, right? Right. Okay, so let's not screw this up this time. we want to get rid of the lower and we want to keep the upper. So it's going to be the same. It's going to be the same thing. We're gonna and the lower half with one. Oh, sorry, we're gonna and it with 1 and then 0 0. Wait, no, that's not fair. Wait, hold on a second.
So
we're gonna want
this probably should be a constant, whatever the operand is.
yeah. It's just you just flip it around, so it's like 1's on the left and 0's on the right, and it's an and again.
Okay. So what this gives us is it gives us this.
Oh, what have I done?
Sorry. That's
Oh no, we're good.
We're good. This.
Phew.
This is our result of our masking operation. Now, there's a small flaw in this situation, and the actual maths that we want to do is byte based. So we've actually got a value here. If we bring this into ye olde calculator, which is actually really ye olde, we actually get this value. So I've clicked in these 2 bits, which is the upper bits here, and we get 6,000 blah 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 blah. But we know for a fact that this is operating on bytes, so this is obviously not fitting in a byte.
Yeah.
So what we want is we want that value down here.
Yeah. So we actually. Oh, that's interesting. Okay, that's cool. That means so we actually want 0's on the left and then the upper on the right, so that we have it in the right magnitude or whatever.
So we have to move it.
Yeah, we have to move it all the way over.
So thoughts?
So we need to move it. Well, we need to shift it by 8. We
Yep.
need to shift it 8 places.
So let's stick that in. So now we have this.
That's what we want. Yeah.
So do you want to? So
Tap that out.
So let's start implementing that, and we'll see how we go.
Okay. Yeah. So I think I feel like we're still gonna do another plus equals because we're just basically turning one 16 byte into 2 8s. This guy goes over here. This guy over here, and then we have to. This is the part where I'm not sure if we'd want to actually use. Actually, why don't we? Yeah, I'm gonna. You know what? I'm gonna do this. No. Yeah.
So you can't really do that because the hash is actually a persistent value that we're adding to across loops.
Right. So I just
So
I
you
just did
actually
it against the whole.
Can't use it as
whole
a
result.
temporary sort of situation.
I was gonna do this, but I felt like it was ugly. Like, but it's obviously more correct to scope it. But the other option might be to like do something like and equals.
No.
No, never mind.
So yeah.
I'm gonna stick with this answer. Scoping.
Yeah. So you have to think about the fact that hash is a value that we're basically
Cumulatively.
we're inserting bits into it as a hash. We're mixing bits into it, and so if you shift the whole thing off 8, you've just shifted off 8 bits of useful data that we had of the entire hash. So that kind of breaks the algorithm. We actually want what we have to look the same. Like we want it to do the same operation as like this on our byte array. We want it to be the same, but we're doing 2 bytes at a time. So anyway, suffice to say, looking at this, let's just go through and just quickly do you want to make any edits to this before I burst a bubble here?
No, go ahead.
All right, let's have a look at what's happening here. So we have our input, which is this. Then we are ANDing by this, which is going to equal this. which we already have the result for, which is this. And which we are then doing a shift 8 on, which gives a result of, if we shift this value by 8, we get...
Wait a minute, it's all zeros.
This.
What happened to our good value?
So you can see the problem. So just work through this and have a think about what we've got there.
Yeah, I'm just trying to go back up to where we actually got the value we wanted. We were ending by ones and then zeros. Or blurb. How about that?
Okay, so the thing about and in fact all of these, so we've got and, or, and XOR, they are all, oh god, what do you call it? Is it commutative? I can't remember the maths term.
Commutative.
You can flip them around and they are exactly the same. So you'll notice, like, if you look at the truth tables for these functions, they're all symmetrical.
Oops.
Like, so we're ANDing two values, and it doesn't matter which order you AND them in, and you still get the same result. Same for XOR, same for OR. It doesn't matter the order. So flipping the order around there does nothing.
And then how come we had... Okay, well, I mean, how do I represent the ones operand and the zero operand? Like, without...
So you've basically done this. You've like taken that and moved it up there. Like, that's what you had, and that makes no difference whatsoever.
Yeah.
So
100%.
So let's... Yeah.
Getting bodied here. No,
right.
I'm just explaining how dumb I feel. Okay, so I know this, and I want to move. I wanted to zero at the right hand side. Oh man. What is the ones and zeros part? This is what I want. Why can't I figure that out? So I'm ANDing. I'm taking the value and I'm ANDing by whatever 1111111100000 is. Oh well, why don't I go back to my calculator and figure that out? Why am I sitting here like this? So it's actually, this is what I want. I'm gonna turn this guy off. I just forgot the constant is FFOOU.
So you can see why they use hex for this, because it's like you get, you know, there's an F, there's an F. Yeah, it like it lines up with the bytes quite nicely. And so as you do a lot of this, you just memorize what these things are.
Yeah, I don't know why I blanked on that. I mean, we literally derived that for the first one, and then I'm like, yeah, I don't have to think about that anymore.
So now we have that, and then we have it shifted down there. So that's correct, but we can make it better.
Okay.
So what you're doing is you are blanking out these ones and getting, you know, zeros in here. But then what we immediately do is shift off 8. So we're actually shifting off all of these off the end and getting rid of them. So we can do that. Does that make sense?
Oh, yes.
Yep, good. So
for some reason, that makes perfect sense. Blah.
So the final thing to do here is now we've got these lines correct. This is right, we've got the lower ones. This is right, we've got the upper ones. Now we just need to merge it into our hash algorithm. And what we know about the original algorithm is that it works on a per byte basis, and it mutates this hash. So I want to hand this to you and just see if we can basically, how would you describe it? Like this is wrong. Like the way that this
order of operations.
Yeah, we've got an ordering issue. So I'm gonna hand it to you and see if we can sort that out.
Well, I feel like we don't want to distribute or shift our bytes and I've done nothing here maybe, but I feel like I have, and this is actually gonna.
Well, remember we had that thing before, and that just deleted all of our bits. If
Just
you
now?
recall. So we've now masked out everything except the lower 8 bits, and then we're shifting the 8 bits off. So that's what happens if you do that. So what I'm going to tell you is this line of code is correct. This line of code is correct. So get rid of that shift 8 that you added just now.
Oh, of course. Yeah.
Yep, so those 2 lines are absolutely correct. So don't change those. These 2 lines are also correct because they came from the original algorithm. So all we need to do is make sure that we're working on a byte by byte basis. So we want effectively this if these are bytes, but we have 16-bit values and we're splitting them out. So effectively each iteration of this loop is going to need to do 2 bytes. Does that make sense?
Yeah.
So it needs to do the lower byte and the upper byte. So how would you modify this code here, like the arrangement of these 4 lines that we have, so that it does this and then it does this again? Does that make sense?
Mm-hmm.
Too easy. Yep, that's exactly right. That is the easy bit. So now we are doing that, and I think I may have the same thing in the Jenkins hash code that I have in River City. Something very similar to that. So yes, so now we have a Jenkins hash for string. We'll just grab it, and now we have a Jenkins hash for string builder. Simple as that.
The string builder like intrinsically. Oh right, because this is actually it. Looping over the internal byte array.
Yes. The internal character array, but yes.
Right. Yes.
Yes. And so yeah, the indexer for string builder is effectively the same. If we look at it, it's the same. Get character at position index returns character. And
Okay.
so the last thing that we wanted to do, and
integer?
I think we're way over time.
Way over time, but that's fine.
Let's try it. Let's take integer. So what we need to know about integer is it is
32 bits.
32 bits, and I'm gonna make a change here. I'm gonna say we're gonna do it for uint, and then everyone who calls it can cast to uint. So it's 32 bits, and so we kind of have to do the same thing we're doing here, but for 32 bits instead of 16 bits. And furthermore, we don't need a loop. Although we could loop, but we'll inline it. I'll just leave the brackets there so it's clear what we have.
Oh, sure. Okay. So this becomes just key. Wait a minute.
Oh my.
Wait a minute.
Sorry, I didn't notice you. Sorry, before we move on to this, you've actually made an error. I just missed it. So my code's correct. So if you just have a look at the string ones you did. I don't know where this crept in, but where you have hash here, it should be key index I.
Oh, yeah, whoops.
Yeah, I think that's just a typo. So
No, I think I mean, yeah, it is and it isn't because, oh yeah, now I gotta oh boy.
yeah, that one has to be uint because the shift needs to be, as we were discussing, it has to be a logical shift, not an arithmetic shift.
Right. Yeah, and I'll just fix that for the string. Okay.
Easy.
Right.
So back to the integer one.
Yeah. I feel like I'm gonna need new const roos here, but this isn't Something more. Something more. I'm trying to think. We had a 16-bit value and we need 8 because we're doing 1 byte or 8. So we did twice to get 8. So we obviously need to do this 4 times, whatever it ends up being. But I don't think any of these number values are correct. But so now we just have to go through this process of calculator. Going, okay, so the first one I want is, let's say the first one I want is just the lowest one. So that's going to be FF.
Well, what? Yeah, F.
Just F.
Well, what you have, if you have F, you have a nibble rather than a byte.
Oh, whoops.
So,
all right. Right. Yeah, we were doing with 8s. Yeah. So my bad. Yeah, I was just thinking about it. Yeah.
But now we know that a byte is two I guess numerals, letters of hexadecimal. So if we wanted the next 16 bits, for example, you could do that, or or whatever sort of pattern you wanted. You can just say F0, F0. So you don't need necessarily. I mean, you can if you like use the calculator to double check your work. But this has a nice property that you can just visually do it. It's like, this is 4 bits, this is 4 bits. This, 2 of them is 8 bits.
Oh, I get you. Okay, right. Okay, so in that case, then maybe this would be like F0. No, poop. I'm gonna check my work here because at least I can. I want the next. Well, this is gonna be the same as the last time, actually. So this is just probably gonna be F. The same thing we had before. Yeah, right. Yeah, I'm just right. Okay, so that.
So you're shifting.
Oh, whoops. Yeah, no, not shift. Yeah, I don't have to do any shifting actually because I don't think. Oh no, wait. Whatever. Okay. Anyway, Brain says, then yeah, maybe I can just throw this in the next one. Next one, do the next one. Now I think I'm missing some shift action here. I could be wrong. Basically, this is oh no, I don't think I need to shift because I'm putting zeros everywhere. I'm only grabbing the part of the 32-bit value that I want.
So we're grabbing the correct part. We're doing, like for the second one here, we're doing this. So this is that, and this is. So we've done this.
Yeah.
But if you recall, we actually want to get this down into the lower section, and then we want to do that for the upper 24 and 32 bits.
Yeah.
But
so we do have to shift.
Pretty close. So we do actually have to do some shifting as well.
Okay. So I think okay. Where to go? Okay. Oh, right. So this one is fine because we're already in the lower one. This one we have to shift. So scopy scopersons, and then this one we have to shift 16. Get it to where we want it, and this guy we need to shift.
Exactly.
All the way to the
exactly.
right.
Now, if we look at color, and we find the right thing. Okay, so packed value. You can see this is the sort of thing they're doing with packed value for this. I guess. Okay, so the way they're doing this is they're just casting it to byte to get rid of the top side of it. But then you can see, okay, to set it, they're masking out the original.
They're masking out the original.
And then they shift the incoming to the right position and then OR it together. So you've got mask out the old stuff, shift the new stuff into the right position, and do a bitwise combine. So that's the same thing we were talking about. Over here, OR is combine and its mask.
Love it.
So the only comment that I make on it, like, this is actually fine. I think most of the time when you're implementing it, you just do it the other way around. You'd probably do key shift 8 and then that, if that makes sense.
Oh, right, because you don't care about, right, we already went over that. Like, you don't care about the those values, but we don't need to account for them and then throw them away. So
Yeah.
that's just try to.
So there's a few reasons for doing it this way. One of them is you don't have to store a massive constant. So like this is this is going to be stored as a 32-bit value. This might get stored as a byte depending on the processor and a whole lot of other issues, a whole lot of other things. So there's like this like super micro optimization for space. It's like I want a shorter instruction rather than one of these. And in fact, I don't recall exactly what the thing is, but you might get an 8-bit 8-bit AND might be separate to a 32-bit AND in IL. So you're sort of reducing the amount of space each instruction takes at every level if you do it this way. And the other thing is it kind of just says, it's like, all right, I want this section of the value and I want it as a byte, whereas this is like it's sort of a grammatical thing, I guess, in a sense.
Yeah.
But yeah,
I think that's the kind of thing I'd probably pick up after practicing a lot.
Yeah, it's also almost like an accent. Like this is how it is done. And there's vague reasons for it. It's not actually that important, but it's just that's what a lot of this code ends up looking like.
The compiler won't save me from myself though in this case, so it's not just style, right?
The compiler I don't think will make a transformation around this necessarily. I don't actually know.
Okay. But it's better to assume it doesn't, or I can use that cool tool that you showed me last time about seeing at the IL.
In fact, maybe we should. We'll just finish off with that sharp lab.io and godbolt.org. So let's have a quick gander about what will happen if I have a public static class like that. I have a method m that's going to take a uint32, uint foo, and return foo and foo shift right 24 xsf, or the other way around, which is return that and oxff0000. I need some u's in here. 4 of these. No, another one for 24. U and shift it 24. And I need to actually return something. So let's have a look at what this results in. So okay, so here we go. So we load constants I42 with this version. Let's copy this over into. Can I have a notepad, please? So there's that one in my little notebook here. And if I switch to this other one, so I'm getting
oh wow.
So I'm getting so I'm getting load constants I4 short version. So this is slightly shorter, and you can actually see this. So this obviously these are offsets in bytes. So this is offset 0 is load argument 0. So that's one. This takes 1 byte. This so the next instruction starts at byte 1. This one takes 2 bytes. So it's the instruction for load a short int 42, int 32, load 24, and so it's 2 bytes. It ends up at byte 3. This one is 4 bytes. Sorry, 5 bytes. It ends up at byte 6 for the next instruction. So you can see that. Although,
well, they both go to 9 at the end of the day.
Interestingly enough, they actually both go to 9. So this load constant here obviously is. Huh. All right. Short. That's weird. I would have expected this to be a .s version. So I don't know what the compiler is necessarily doing there, because I think that could be done with a load short, but maybe I'm reading the instruction, reading this one wrong or something. Yeah, so it's going to give me mass over. So anyway, hopefully you know enough about reading this. Is load argument 0, load constant 32-bit integer short version, load constant 32-bit integer, shift right unsigned. So this is the unsigned versus arithmetic that we were talking about before, and obviously ands the two values, and returns the value.
Right.
So let's just jit it and see what it does. So as you can see, so it's a much shorter. It's like move it into a register, shift that register, and that register, return that register.
Combine.
Very simple.
Yeah, it's literally what we're doing there. It's like one instruction per instruction.
Let's see if this is any different. No. So that is one thing about what am I? Intel instruction set. It's actually it's x86. Anyway, there is no instruction for there is no load constant short in a lot of cases for this. It's just you take the 32 bits, no matter whether you do it that way around or this way around. You can see it's the same length. We're ending up here. So this is effectively stored as that, and same for this. Does that make sense?
Well, other than where the zeros just went there, isn't it 18 0 0 0 0?
Yeah. Okay. So what I've done is I've just inserted the padding bits.
Right. It's because it's going the other way around. Yeah.
So you can see
the shift and the and are flipped.
Actually, am I right there? I think I'm right there. 2, 3, 4, 5. Oh, maybe I'm not.
So that one goes
I'm wrong. I'm wrong. There is actually short versions of these instructions. Because this is like
technically
2, 3, 4, 5. Yeah, this is only 3. This is only 3 bytes.
Yeah, and the other one was 5.
And this one's 5. I was wrong. My mistake. Although we seem to end up at the same place.
Yeah, I don't know enough to understand why we have more. We're storing more, and that's what you expected, that we'd be storing more.
What is it? Anyway, this is the thing. It's like I actually don't program in x86 assembly, so I am not fluent enough to tell you too much details. But suffice to say, there are different
But I can just do the nice and concise one, because A is what everyone expects, and B is less to type. And
yes.
It's just.
So
and it turns out it may be 2 bytes less in the numbers in the storage, so why not do it?
Certainly, when you do a lot of this, yeah, it is less. I'll skip the God bolt for now, because we just did that. We just jittered it, and that's the output. So one reason why it may in fact be less is like you might not be doing hands and shifts. You might be doing a different sequence, and so you want the shorter one. But that's generally like you almost never care about that. But yeah, so the fact that everyone expects this is the main reason to do it this way.
Yeah, that's a good reason.
Okay, so I think seeing as we're massively over time at this point, we should wrap it up. So thanks for watching, everyone.
Yeah.
We've got our hash functions, and so next time I'm going to delete all this, so hopefully you got everything you need from that and all of that. So next time we come in, we'll actually use these for something useful. So thanks for watching, everyone, and we'll see you next time.